Welcome to this lecture on energy conversion and storage techniques. So today in this lecture we are going to continue on energy units and conversion. So in our last lecture we have seen about the different types of energy which is being produced from thermal, electrical, electrochemical energy production devices and the storage devices, and the different terminologies which we use to express the energy in the particular scenario in the particular devices. And we have seen about different types of energy flux, the energy conversions, for example, from joule to BTU, from joule to calorie, from joule to erg, and you have seen about CG system as well. So in today's lecture, we are going to be seeing about the units of renewable energy systems, which we get, for example, like solar, geothermal, ocean, biomass. So how energy is expressed in these particular systems. So in the first system, we are going to be seeing about solar radiation. So how do we quantify a sunlight? So there are many different terms to use. The first terminology is solar irradiance, which is the instantaneous power, the amount of energy which is obtained per square meter in watt per meter square. The other one is solar insolation, that is the energy over time. So you have the concept of time entering into it. So you have joule per meter square or watt hour per meter square or kilowatt hour per meter square per day or per year. The third one is beam radiation, which is the direct amount of energy which is obtained from sun. So it is the solar radiation arriving directly from the sun. Fourth one is diffuse radiation. So any radiation which comes from your sun or solar, a part of it gets reflected back and only a part of it is gets diffused through our atmosphere and reaches us. So it is the solar radiation scattered by the atmosphere. And the last one is your global radiation, which is the sum of your beam and diffuse radiation. So all these things are expressed in terms of watt per meter square or joule per meter square or watt hour per meter square or kilowatt hour per meter square per day or per year. So this value, it varies with respect to your region, state, nation, countries, the time of the day, the time of the year, the seasonal variation, everything varies with respect to the time you measure it. Next one is the units which we use in our geothermal energy, which is basically the internal energy of our earth, which is getting transferred into fluids. So first concept is about geothermal gradient. So gradient refers to the change. So it is a rate of increase of temperature with depth in the earth's interior. So how much temperature difference is there for every kilometer we go deeper into the earth. So it is expressed in terms of degrees Celsius per kilometer. The next one is a heat flow, the rate at which thermal energy is transferred from the Earth's interior to its surface. So this is expressed in terms of watt per meter square. So our surface is the Earth's core has got a very high temperature which gets diffused into your Earth's surface. So the rate at which the energy is getting transferred from the Earth's interior to its surface is measured in terms of watt per meter square. The third one is enthalpy. So it is a thermodynamic property, represents the total heat content of a geothermal fluid. It is measured in terms of joule per kg. The next system is about your ocean energy, how you are harvesting your marine power. So you have three different things in that. One is a tidal energy, wave energy, and your ocean thermal energy. So tidal energy. So it is the tidal energy is the difference between the high and low tides in meters. Another one is about head of water, also in terms of meters, and basin area in terms of meter cube or volume. So energy potential is often expressed in all these systems in terms of kilowatt hour per tidal cycle. And next one is wave energy. Important parameters are the wave height in terms of meters and the wave period in seconds. So number of waves per second. So it is energy flux of waves often expressed in kilowatt per meter of wave crest. The last one is a ocean thermal energy. So when it comes to thermal energy, of course, you're going to have your temperature and your temperature difference. So it is the temperature difference between the surface and deep ocean waters. Your last of your energy from renewable sources is your biomass energy. So biomass plays a major role as an energy source because of its high carbon content. It has got the highest carbon content on our planet Earth. So it plays a main source of energy. So biomass yield. So biomass basically is any organic matter. So it is the amount of biomass produced per unit area. So tons or hectares per year. And from biomass, we have various products such as bio oil, biochar, biogas, bio oil, and many, and we have products even such as ethanol. So one important thing is about a biogas production. So it is a gaseous product. So meter cube per kg. So how much of biogas is produced per unit mass of your biomass? So that is expressed in terms of that. Next one is your energy content of biomass, also called as the calorific value or heating value. So it is expressed in terms of joule per kg or calorie per kg. Since it is a little bit relatively higher value, it is expressed in terms of megajoule per kg. Okay, so we have seen about many of these derived and related units. So just a review of those. So derived units provide valuable insights into the performance, efficiency, and scale of the energy system. Specific energy and energy density are critical for energy storage comparison. So specific energy is related to your per kg or per mass, and energy density is related to your volume. So these play a major role, especially when, because for example, in electric vehicles, you have a relatively little amount of volume available for a storage of your batteries there. So the battery which you design has to fit within that particular space, and it should have maximum weight of so and so kgs. So then this specific energy and energy density needs to be high for a particular application. Heating value quantifies the potential of fuels. So a fuel, let's say petrol or diesel on combustion produces so much of energy. So that energy is what is used to drive your motors. So there your heating value plays a major role. Macroeconomic indicators help understand your energy economy relationship. Specialized units, as discussed in the last two slides, they characterize your renewable energy resources. So what are the importance of accurate conversions? So when you're working across different fields and regions, often we require the converting various energy units. So this accuracy plays important term in avoiding errors in calculation, comparison, and decision making. So initially we do the calculation, and when you want to compare two or three systems within the same category or different categories, you have to compare it and maybe do energy conversion. And final thing is in your decision making. So we always use a reliable conversion factor from reputable resources. So now we will just have a brief outline on the conversion values. So first one is a joule based conversion. So we have all seen about these things in our previous slides. Just a recap. So 1 watt hour is equal to 3600 joules. 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. So 1 watt hour, R refers to 3600 seconds. So kilowatt, so automatically we get 3.6 into 10, 6 joules. Next one is BTU. 1 BTU is equal to 1055 joules, and 1 calorie is equal to 4.184 joule. So coming to your power conversions, 1 kilowatt is equal to 1000 watt, 1 megawatt is equal to 10 lakh or 1 million watt, 1 horsepower is equal to 745.7. This is a mechanical horsepower. If it's an electrical horsepower, it is 746 watt. Next one is your conversions involving specific energy and energy density. So 1 megajoule per kg is equivalent to 277.8 watt hour per kg. So here it involves conversion from joule to watt hour. When you're converting watt hour per liter to megajoule per kg, 1 megajoule per liter is almost equivalent to 277.8 watt hour per liter. So a key important thing is when you're converting mass based to volume based units, you need to have a knowledge on the density of the storage medium of fuel. So first line it talks about watt hour per kg, whereas second line talks about watt hour per liter. So different materials have different densities. For example, if you take water, the density is 1000 kg per liter. Whereas if you take a gaseous system, let's say air, the density is 1 kg per liter. So you have a huge difference which depends on your storage medium. So when you're talking about fuel also, knowledge on the density of the fuel plays a major role. Okay, so next one is about your temperature conversions. So Celsius, we have three different units, your Celsius, Fahrenheit, and your Kelvin. So Celsius ranges from general, when you talk about liquid, it varies from 0 to 100. Water, it stays in the water format from 0 to 100 at atmospheric pressure. The 0 degrees Celsius corresponds to 32 Fahrenheit, and the 100 degrees Celsius corresponds to 180. So that's how you get the second point. Fahrenheit is equal to Celsius into 9 by 5 plus 32, because 0 degrees Celsius corresponds to 32, and your 100 degrees Celsius corresponds to 180 Fahrenheit. So you get the relation degree Celsius equal to degree Fahrenheit is equal to degree Celsius into 9 by 5 plus 32. The exact opposite is given in your third point. Degree Celsius is equal to Fahrenheit minus 32 into 5 by 9. Now when you want to compare your Celsius and Kelvin scale, Kelvin is equal to Celsius plus 273.15. So that 0.15 gives a accurate value. The last statement, temperature differences are the same in Celsius and Kelvin. So when you say you have a 100 degrees Celsius difference, let's say one system is at 10 degrees Celsius, the other system is at 110 degrees Celsius. So the difference works out to be 100. Now when you convert the entire scale to Kelvin, the temperature difference is from 270 to 83.15 and 383.195. When you talk about 0 to 110, 10 to 110 degrees Celsius, it corresponds to 283.15 to 383.15. So the difference there also works out to be 100. So when you're discussing about degree Celsius and degree and Kelvin, the temperature difference is same. Whereas this is not the same with your Fahrenheit scale. Your degree Celsius difference, if you say from 0 to 100, in Fahrenheit it will be from 32 to 180. So the difference is very different. So the temperature difference is not the same when you are doing conversions between Celsius and Fahrenheit or between Kelvin and Fahrenheit. Next one is relevant for compressed energy storage. So till now we have been seeing mostly about um, normal atmospheric pressure. When you're talking about at higher pressure, especially it applies for compressed air and gaseous fuels. So we have many different units. One is Pascal, one is bar, and one is atmosphere. So basic unit is your Pascal. The amount of force which is exerted per unit area. So that's how you get Newton per meter square. So force is in terms of Newton and area is in terms of meter square. So 1 Newton per meter square, 1 bar refers to 10 power 5 Pascal. 1 atmosphere refers to 101, sorry, 1 lakh 1325 Pascal. So when you convert that into a bar scale, it is 1.01325 bars. Now we have one more unit is pounds per square inch. So when you convert this 1 Pascal or 1 atmosphere, you get 14.7 psi. So this psi term is very commonly used in your vehicle air pressures. So the pressure of your wheel or your motorbike, so it will be probably around 29, 33, 40. So this will be the approximate value. So from that you can see your pressure inside your bikes or cars will be around 2 to 3 bar pressure will be there in your vehicles. So this pressure unit is crucial for compressed air energy storage or other pressure related energy technologies. When you talk about storing of cylinders, gas in cylinders or hydrogen, we are talking about much higher pressures. Like for example, a nitrogen gas cylinder, it is pressurized up to 150 atmosphere or 150 bar. So that is your average values. When you're talking about higher systems, you have even up to 250, 300 bars of storage. Next one is about your flow rate conversions. So this is applicable for your hydropower and wind. So volumetric flow rate is the cubic meter per second, meter cube per second, or your liter per second. And when you talk about your mass flow rate, is going to be about kilograms per second, kg per second. Now, when you want to convert again from volume to mass or mass to volume, your density plays a major role. So multiplying it or dividing by the particular density can help you get the alternate unit. So this applies to your wind, especially wind air flow rate. Whereas when a hydro comes to hydropower, it's going to be a volumetric flow rate. Next one is your efficiency. Efficiency. So efficiency is basically your output by input. So it is defined as the ratio of the useful energy output to your total energy. So this is used in all your energy storage or energy conversion devices. When it comes to energy conversion, the input energy will be in a particular form. Output energy will be in a different form. So the output energy divided by input energy. From thermodynamics, we know that no system can have efficiency of 100. It will always be lesser than 100 due to losses in terms of heat or any other form. However, we can achieve maximum up to 100. So it can be expressed as a decimal or percentage. So when you express a percentage, the output by input into 100, so you get 85 or 75 or 60. Whereas when it comes to the decimal, it is only the output by input. So output is always lesser than your input due to losses. So your value will be less than 1. And the overall value can range between 0 and 1 if it is expressed as a decimal. If it is expressed as a percentage, it can vary between 0 and 100. So it is a unitless term because it is the energy by energy. So it is crucial for evaluating the performance of energy conversion and storage systems. So especially when it comes to energy conversion, energy storage, how much energy is given for storage of that particular unit of fluid or something, and how much energy is got out. So that's how you evaluate your energy storage system. Next one is your load matching and unit considerations when it comes to your solar PV. So in solar photovoltaic system, load matching involves ensuring the power output of a PV array meets the demands of the load. So units must be consistent when calculating the number of solar cells or modules required to deliver a specific output at a certain voltage. Watt and volts ratings of integer components and overall system must be carefully considered. So when you talk about photovoltaic system, it involves use of multiple PV arrays, basically photovoltaic panels. So each panel will be rated at a particular voltage and it can give up this much amount of load. It can withstand this much amount of load. So when you want a higher voltage system, let's say each PV array can give 4 volt, but when your requirement is 20 volt, you can have 4 arrays in series. Or if you want a more powerful system at same voltage, you can have the system in parallel. So that's why we have two terminologies. One is your specific power output and voltage. So these things should be matched exactly depending on your uh, the power rating of your particular panel. Next, we are going to go into something called as greenhouse gas emissions. So when you're talking about energy, you are going to have, um, especially when you're going to talk about fuels, you're going to have amount of energy which is given out in terms of carbon dioxide, which results in greenhouse gases, or in terms of heat, or in terms of pollution. So everything has to be calculated in terms of a particular a specific unit for consistency. So everything is equated to the grams of carbon dioxide equivalent per kilowatt hour. So whatever be the emissions you have, whatever be the drawbacks you have, everything is converted into the specific greenhouse gas, carbon dioxide. So it is used to express the greenhouse gas emission associated with generating 1 kilowatt hour of electricity from a particular source. So to generate 1 kilowatt hour, how much equivalent of grams of carbon dioxide is given out? So when you have this common system, you can easily compare different systems along with any other system to find out what is the environmental impact of that particular system. Another terminology which is used is tons of CO2 equivalent. So it is used to quantify the total greenhouse gas emissions over a period. Let's say the amount of CO2 equivalent emissions over a year. You will find this terminology even mentioned for different modes of travel. So a railway mode of travel from this place to this place, your travel is equivalent to so many kgs of CO2. If you travel by flight, this is the equivalence. If you travel by a motorboat, this is the equivalent. So this is another terminology they used, especially to consider the amount of the greenhouse gas equivalence of greenhouse gas emissions of that particular mode of transport. So this plays a major role when it comes for your carbon credit calculation, the efficiency of the process or the work done by the particular organization towards the environment, the benefits of the particular technology, all those things play on this particular unit. And next one is life cycle assessment. So what is life cycle assessment? It evaluates the environmental impacts of a product or process throughout its entire life cycle. So let's say as a system is there from the time of its production up till its useful age, and then for its final decomposition or degradation or return back into environment, what are the entire process. So you do a complete analysis of the life cycle of the particular product and you give out in terms of different units. So one unit is your COT equivalent, and the other unit is your cumulative energy demand in megajoule per kilowatt hour, the total amount of primary energy consumed throughout the life cycle of a technology. So two units play an important role. CED, that is the cumulative energy demand in megajoule per kilowatt hour, and the next one is your emissions in gram CO2 per functional unit. Now we have come to the last one, which is the energy payback period. So it is a time-based unit. So the time required for an energy system to generate the same amount of energy that was consumed in its production, installation, and disposal. And it's measured in years. So a shorter EPP indicates a more sustainable energy technology. Okay. So we will have a short review of what we have seen in this entire session. So we started off with what is a unit, why is its conversion matter, so how it is quantified, and why it is useful for its comparison, the foundation of the calculation. So it is used in your engineering design, efficiency analysis, and economic evaluations in the energy sector. And it is very much essential in facilitating the communication among scientists, engineers, policymakers, and public. Then we saw about the international system of units, that is joule, and joule per second is called as a watt. So, and beyond this SIS system, you have your BTU, foot pound, CGS system, and horsepower. So depending on the sector, a different unit is being used, and the perils of unit confusion. So usage of wrong units and incorrect conversion factors can lead to significant errors in calculation and analysis. So in policy and economics, the inaccurate energy data can lead to a flawed decision making. Then we saw about your different units such as a joule. Then we saw about your watt hour. Then we saw about your BTU. So BTU is the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. A similar terminology is a calorie. So 1 BTU is equal to 1055 joule. A calorie is amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Then we saw about your electron volt, the amount of energy gained by the charge of a single electron when it moves across a potential difference of 1 volt. Then we saw about your erg and pound foot, how it is used in the CGS system and imperial system. Then we saw about a unit which is specifically used in your natural gas industry, which is your therm, especially in the United States. And finally, we saw about your barrel of oil equivalent and ton of coal equivalent. So this is about your fundamental units. Then we saw about another important unit, which is a horsepower. Mechanical horsepower is 245.7, 746 watt is for your electrical horsepower. It is used to rate the power of engines and motors and other mechanical devices as well. Then we went on into energy flux. So it is a watt per square meter with respect to area or kg or volume. So some of the examples were power density, then kilowatt ampere. Then we saw about the power unit in renewable power systems. And in detail, we saw about solar radiation units. Then we saw about other units used in your ocean and your biomass and geothermal. Finally, we saw about the importance of your accurate conversion. Then we saw about the common conversions, joule to kilowatt hour, joule to BTU, joule to calorie. Then we saw about your energy density and specific energy calculations. Finally, we saw about the temperature calculations and flow rate calculations. At the end, we saw about the terminology efficiency and its unit. And towards the end, we saw about greenhouse gas emissions, about the use of CO2 equivalent per kilowatt hour, and life cycle assessment and energy payback period. So these are the references from which we have taken the material used in this presentation. Do check these links for the updated information and for more enhanced knowledge. Thank you.